Good evening, everyone. Today I will discuss about the electrochemistry of the third class. So in this third class, basically we will know about the Nernst equation, derive how we can derive the Nernst equation in various way. There is some relations between uh, Nernst equations with Gibbs energy and the activity terms and also the equilibrium constant. Okay, so there are the several terms is there in thermodynamics, and these terms how is related with this Nernst equation. That is the very important here, that we will know after the few minutes. But whatever I have taught in the previous class about the Nernst equation, if I revise that part, so what will be happened in that case? So basically, we have taken a galvanic cell, which is the zinc, sorry, which is the copper plus 2 copper and zinc to zinc plus 2. This like that actually. So this is the cell, this is the galvanic cell, where we can say or we can write in this way. So here actually basically I have written this cell. This is written as a reduction, this is written as oxidation. So this is actually not a right way to retain a chemical cell. You have to return always, a cell in a reduction way. In a reduction way, and whatever value will be given in this question, that also the reduction potential, so whatever we have to write, that will be in reduction. If we see the reduction potential, curve, there basically where we have taken this hydrogen cell, this if I taken this reduction where this H plus plus electron is giving to half of H2. Okay, so this is the hydrogen cell. So this, according to this hydrogen cell, this reduction potential equal to E0 cell equal to 0. Okay, so we have taken this is a standard cell. So according to this cell, if we see the reduction potential, there is the positive value, positive reduction potential value, and there are some negative reduction potential value. Okay, so this positive reduction potential value, what is the means of the positive reduction potential value, and what is the negative reduction potential value? So this is the very important thing. So this positive reduction potential value, when a electrochemical cell is showing a positive reduction potential value, that means it is a weak oxidizing agent. And when a reduction potential value is the highly negative, so this is a strong, sorry, uh, sorry. So this is will be a reducing agent, weak reducing agent, and when it will be the when a electrochemical cell will have a higher the negatives value, higher the negative reduction potential value, then it will call a strong reducing agent. Strong reducing agent. So that means it can reduce the other species easily, and it will be the oxidized to itself. So that is the thing. According to the hydrogen cell, here we have taken this hydrogen cell as a standard. So at a all temperature, and the concentrations will be the unique. Okay, so the at a unit concentration at all the temperature, the E0 cell of the hydrogen is equal to 0. So here we have taken this hydrogen cell as a standard cell. So according to the cells, whatever the reduction potential of the others, the half cells will be the decided the value. Once we will get the positive reduction potential value, then that means that it is a weak reducing agent. That means it's a strong oxidizing agent. And when we will get the more higher the negative value, higher the negative reduction potential value, then it is a strong reducing agent. It will reduce this in other species easily. Okay, so it is a strong reducing agent. Like that, we can say that we can say, for example, the potassium graphite. uh, Potassium graphite, here the potassium is taken, the potassium plus is taken, one electron is goes to the potassium. Okay, so here it's the reduction potential value minus 2.98. So it is a higher negative reduction potential minus 2.98. Okay, so what will be happened for that case? The reduction potential value is minus 2.98. Okay, so for that potassium case, it is a strong reducing agent. It can reduce this another species easily, but it will be simultaneously, it will be oxidized to potassium plus. So potassium to potassium plus electron, that means it will be the oxidation reaction. So another reaction will be the reduction reaction. Okay, so suppose I have a mixture of, suppose there is a mixture of nickel plus to a metal complex is there. Okay, so this is a metal complex, this is a nickel plus to metal complex. So if we treat this metal complex with this potassium graphite, so what will be happen that, so it is a strong reducing agent. So it will reduce this nickel plus to nickel 1 or the nickel 0. Okay, so it will reduce this nickel plus to nickel 0 or the nickel plus 1, and it this potassium will oxidize to potassium plus 1. So that's why there are the some literature, there are the some the research paper is there where the potassium graphite is used to reduce this nickel plus to complex to nickel 0. So this is a low valent chemistry, this is a low valent transition metal chemistry. There the nickel 0 is formed, is produced by the reducing agent. This is the potassium graphite, with this potassium graphite, because the potassium graphite has a higher negative reduction potential. So when it will have the higher reduction potential, negative high reduction potential, that means the oxidation reactions will be the favorable. The oxidation reactions means it will be oxidized, it will be oxidized. So potassium to potassium plus 1 will be easily formed. Okay, so oxidation reactions will be favorable. That means this potassium, here the potassium act as a reducing agent. In the redox chapter already I have said that whence a reduction reaction is happening by this metal, whatever metal is involved in this reduction reaction, so this metal actually is a oxidizing agent. Whence a oxidation is reaction is happening here, you see that this potassium to potassium plus ion is forming, potassium to potassium plus ion is forming. So here the potassium is oxidized to potassium plus 1. So this is a oxidation reaction. So this is a oxidation reaction. Okay, so in this reaction potassium is involved. So here the potassium actually it can act as the strong reducing agent, the strong reducing agent, because it has the reduction potential minus 2.98. It has the higher the negatives value. Okay, so this is there are some books is there, or the internet you can search the reduction potential table. Whatever we will see the positive value positive value, that means it is a weak reducing agent, and negative value, it is a strong reducing agent. Okay, so with this concept, I am going to discuss about the Nernst equation. Okay, so this is a very important thing. Whatever is there, just I have taken a galvanic cell, it is a common galvanic cell, zinc to zinc sulfate, and there is the copper sulfate to copper. So this is a galvanic cell. So here this is a LHE and this is a RHE. That means this is the left hand electrode, this is the right hand electrode. So in this left hand electrode, oxidation reaction will be happened. So what is the oxidation reaction is happening here? That is the question. Okay, so the oxidation reaction is happening zinc plus 2 electron. So what the reduction reaction will is happening in the cathode reaction. Okay, in the cathode electrode. So so this is a right hand electrode, that means it is a cathode. This is a left hand electrode, that means it is a anode. In anode, the oxidation reaction will be happened. Cathode, the reduction will be happened. It is a negative charge and it is the positive charge. Okay, so reduction reaction, what is the reduction reaction is happening? This copper plus 2 is taking the 2 electrons and forming this copper. So this is a one half cell reaction, this is another half cell reaction. So total cell reaction, what is the total cell reaction? Total cell reaction is zinc plus copper plus 2 is forming. So these two electrons will be cancelled. Copper plus so this is a total cell reaction. Okay, so according to this total cell reaction, we can write the Nernst equation: E cell equal to E0 cell minus RTNF, okay, into 2.303 log concentration zinc plus 2 concentration copper plus 2 concentration zinc. So this concentration, concentration of the copper and the concentration of the zinc at the standard conditions, it will be the 1. So E0 cell equal to RT by NF into 2.303 log concentration zinc plus 2 by copper plus 2. Now if we calculate, if we solve this equation, what will be the thing? 0.0591 by n into log zinc plus 2 by copper plus 2. So E cell equal to E0 cell, but E0 cell, so here we can write also the E0 cell equal to E0 R minus E0L. That means right hand, that means the cathode. So the reduction potential is 0, copper plus 2 by copper minus E0 zinc plus 2 by zinc. So whatever potential value will be given in question, that is the reduction potential. Okay, so E0 cell equal to that one. Okay, you just put the value here and the calculate the E cell of the reduction potential of the total cell with this concentrations value, and n is the number of electron. Here n equal to will be the 2, here the n equal to the 2. So this is the Nernst equation for that galvanic cell. This is a standard galvanic cell, that's why I have taken that galvanic cell. Okay, so from that electrochemical cell, from that Nernst equation, we can convert it. We can convert it, this Nernst equation, as a activity forms. Okay, where we can say that 0.0591 by 2 into log this concentration term we can write here as a activity, where the activity coefficient will be the 1. Where we know that this activity coefficient, when the activity coefficient will be the 1, then concentrations will be is equal to the activity. So here the activity zinc plus 2 by activity copper plus 2. Okay, so in this way also we can write the Nernst equation. So this is the thing. So this is a One's law where we have expressed the Nernst equation as an activity term. Okay, so this is the fundamental thing. Now, if we write the Nernst equation with the equilibrium constant. Now, how the equilibrium will be the coming, that is the very important thing here. So, if we see the previous slide, the equation is the galvanic cell equation is zinc plus copper plus 2 is going to the zinc plus 2 plus copper. So what is there? What is happening in this reaction? That is the very, very important here. Here, if you see this copper, so this concentrations will be 1, this concentration will be 1. Just I am taking the concentration of the copper plus 2, that is the effective, and the concentration of the zinc plus 2, that is the effective. So here I am considering only the concentration of the copper plus 2 and the concentration of the zinc plus 2. So what is happening in this reaction? The concentration, when this chemical reaction is happening, then we are getting the current. We are getting the current. There is a voltmeter. It is showing some value. It is showing some value. That is the current value. It is the swing. Okay. How much the current is appearing from this redox reaction, that is the thing. Now, if during the reaction, what is happening here? During the reaction, the concentration of the copper plus 2 is a decreasing, and the concentration of the zinc plus 2 is the increasing. But according to this reaction, when this reaction is happening, we are getting the current. So after few times, the copper plus 2 concentrations will be the decreasing. So the current will be also the decreased. We will not get the sufficient amount of the current. Whatever amount of the current we got at the starting point of this reaction. Okay, so this amount of the current we will not get because the copper plus 2 is reduced to the copper. So here the concentrations of the copper plus 2 is the decreasing. So at the sometimes, after the sometimes, what will be happen? We will not get any current. We will not get any current. That means that the concentration of the copper plus 2 is equal to the concentration of the zinc plus 2. Okay. So what is happening here? What is happening if we understand that condition? What will be happened? So there are a bucket. So suppose there is some amount of the water is there. It is the level of the water is here, but here the level of the water is here. There is a stopper system is there. Okay, when we open this stopper, some amount of the water will go to from that side to that side. But when the level will be the same of the two buckets, then there will be no flow of the water. Okay, so there will be no flow of water because the level will be the same. Similar thing is happening here. When the concentrations of the copper plus 2 is equal to the concentration of the zinc plus 2, then there will be the no flow of current. That condition is called equilibrium constant. Equilibrium condition. So in this equilibrium condition, we can express the equilibrium situation as equilibrium constant. The equilibrium constant is happening in that case, in that reaction, concentration of the zinc plus 2 by copper plus 2. Okay, the ratio of the concentration of zinc plus 2 and the copper plus 2 is expressed the equilibrium constant. So this is the equilibrium constant. Okay, now the question is that, so at the equilibrium situation, the concentration of the copper plus 2 and the concentration of the zinc plus 2 is equal. Now for that electrochemical cell reaction, what will be the Nernst equation? So E cell equal to E0 cell minus 0.0591 by 2 log concentration of the zinc plus 2 and concentration of the copper plus 2. So this is a Nernst equation for that electrochemical cell. But what will be happened here? So we are saying that there is this there is at the equilibrium constant there is no flow of the electron. Okay, sorry, there is no flow of the current. Voltmeter is showing the 0, so there is no current is flowing. So that means the E cell equal to 0. E cell value equal to 0, but E0, you see, this is the E cell, what will be the calculated from that electrochemical cell, and E0 cell is the standard electrode potential for that cell. Okay, E0 cell equal to E0 R minus E0 L. Okay, so the value of the E0 cell is a standard that will be calculated from the standard reduction potential value of the each half cell. Okay, so here at the equilibrium constant, at the equilibrium condition, E cell equal to 0. So E cell equal to 0, that means E0 cell equal to 0.059 by 2 by log. Now this term is equivalent to E K equilibrium, because the equilibrium constant is equal to the ratio of the concentration of zinc plus 2 by the ratio of the copper plus 2. So here we can say also, so this is the equation where we can correlate the Nernst equations with the equilibrium constant. Now if E0 cell value, now the E0 cell value for that the galvanic cell equal to 1.1 volt, 1.1 volt. Okay, so 0.059 by 1 by 2 into log K equilibrium. So from that equation, K equilibrium will be 2 into 10 to the power 37 at 298 Kelvin. Okay, so at this temperature, the equilibrium constant value will be 2 into 10 to the power 37 value. So in this way, we have to calculate the reduction, calculate the equilibrium constant from the Nernst equation. You just remember that at the equilibrium constant condition, E cell will be 0. Okay, so because the concentrations of the zinc plus 2 and the concentration of the copper plus 2 will be the equal, so there will be the no flow of the current. That means the E cell will be the 0. So when the E cell will be the 0, so E0 cell will be the 0.059 by 2. Here the 2 means the number of the electron is involved. Okay, so this is the thing. If we consider a electrochemical cell, copper plus 2 Ag plus aqueous equal to copper plus 2 aqueous plus 2 Ag solid. So in this electrochemical cell, it is written that E0 cell equal to 0.46 volt. Okay, 0.46 volt. So what will be the equilibrium constant? So when they are asking about the equilibrium constant, that means you have to consider at the equilibrium condition. So at the equilibrium condition, what will be the equation for that electrochemical cell? So E0 cell equal to 0.0591. Now in that case, in that cell also the n equal to will be 2, the number of electron will be the 2. Okay, so 2, and it will be the log, and the concentration of the copper plus 2 and concentrations of the Ag plus whole square. Okay, so 0.059 by 2 into log, that is the equilibrium constant, and this value will be 0.46. So from that, K equilibrium equal to, if you calculate that equation, we will get the value 3.92 into 10 to the power 15. So this is the equilibrium constant value for that case. When in the question we will ask the equilibrium constant, that means the equation should be in the electrochemical reaction is there in the condition of equilibrium condition. Okay, so this is the condition of the equilibrium condition. So after that, we will discuss about how the relation between Gibbs energy and electrochemical cell. Okay, so there is a relations between the Gibbs energy and the electrochemical cell. Now, the electrical work, whatever electrical work that is done in 1 second is equal to the electrical potential multiplied by the total energy passed. So if you want to obtain the maximum work from a galvanic cell, then the charge has to be the parts reversibility. So here what is happening, the reversible work done by a galvanic cell is equal to the decrease in the Gibbs free energy. So if we designate the Gibbs free energy for that cell, the delta Rg, okay, is equal to minus NF E cell. That means that this is the electrical energy. Okay, so this electrical, when this electrical energy is multiplied by the charge, we will get the Gibbs free energy. Okay, so this is a formal condition. So this is the, for the formal condition, we can write the equation of the Gibbs free energy with the E cell. Now for that case, for the equation of whatever, suppose I have taken an example, 2 zinc plus 2 copper plus 2 aqueous. Okay, so if I express the equation, suppose from that equation we do not know actually how many electrons is involved, because this is the n for the number of electron and this is the Faraday constant, this is the 96.500 coulomb. That is the point I will come later how this F value is coming. But n is equal to the number of electron. So how many electron is involved in this redox reaction, that we have to know. So to know the how many electron is involved, we have to express the equation like that: 2 zinc plus 2 equal to equal to 2 into 2 electron. Okay, similarly copper plus 2 is going to the copper. So here we need the 2 electrons, but we are multiplied by the 2, so it will be the 2 and it will be the 2. So what is happening here? There is the 4 electrons involved in this reaction. So in this reaction there is the 4 electrons involved. So for that reaction, the delta Rg equal to minus 4 F E cell. So this is a formal condition. In that formal condition, we will get the equation. But at the standard condition, if the concentration of the all the reactants specified is the unit, okay, then delta R0 equal to minus NF E0 cell. Okay, so this is the equation. Now we know also from the thermodynamics, we also know that delta Rg equal to minus RT ln K. Okay, so this is also the equation. So in that case, if we equal, this previous reactions will be calm. So this minus will be cancel out. So E0 cell will be RT by NF. Okay, RT by LF LK. This is the equilibrium constant. So from that equation we also write the relations between the E0 cell and with the equilibrium constant. Now suppose there is a, so this same reaction I am taking zinc plus copper plus 2 aqueous. Is the zinc plus 2 aqueous, this one. So for that case we know that E0 cell equal to 1.14. Okay, so delta RGG minus NFE0 cell, we know that equation. Okay, so in that equation we know N equal to 2. So minus 2 equal to 96500 into 1.1 volt. Okay, so what will be the volt? Volt, this is the volt, and that the unit is the coulomb per mole. Okay, this is the mole inverse. Okay, so what will be the value? 21227. This is the volt into coulomb, that means the joule into mole inverse. Okay, so if I write that equation at a kilojoule, so that will be the answer. So kilojoule into mole inverse. So in that way we will get the question in various type of the competitive exam. They will ask to calculate the delta G0 value. They will ask also the equilibrium constant value from the non-stick equation. So in this way we have to calculate, and also we have to know the relation. That is the important point. Okay, what condition is there and what equations will be implied in this reaction, that is a very important. Now after that I will discuss about some important thing, that is a very important. This is a electrolytic cell and the electrolysis. Okay, how this Faraday's law is coming, that is the important thing in this chapter. And also already I have said in the previous class also, in that content just I am saying that for the spontaneous reaction, okay, for the spontaneous reaction always the delta G value should be the negative. Okay, already I told, but again I am telling that for that formal condition, but from that standard condition delta G0 will be the negative. But from that condition, from that equation, delta G equal to minus NFE0 cell. Okay, so to be the negative value of the delta G0, this E0 cell should be positive value. Okay, so that should be positive for a continuous reaction. Okay, so when the delta G equal to the negative, then it will be the spontaneous reaction. But when the delta G equal to the 0, that means it is a equilibrium. When the delta G equal to give the positive value, this is a non-spontaneous reaction. This is a non-spontaneous reaction. Okay, so this also will be the very important for that MCQ. Just they will give the some E0 cell value of the half cell, then we have to say for that cell it will be spontaneous redox reaction, or it is non-spontaneous, or this reaction is at the equilibrium. Just you calculate the E0 cell. E0 cell equal to the E0 R minus E minus L. So E0 R minus E0 L. From that value, if it is a positive, suppose this E0 cell equal to the positive value, it is the giving the positive value. So it is a spontaneous reaction. When it is the giving a negative value, the non-spontaneous reaction. When it is going to the 0, that is the equilibrium. Okay, here the concentrations will be the reactant and the product is a same. Okay, equal. So that condition is called the equilibrium constant. Okay, so from that equilibrium condition it can also the calculate the equilibrium constant. Okay, so these are the things that are very very important for that electrochemistry chapter. Okay, now next is that electrolytic cell and the electrolysis. That is the important thing. So first we have to know about the electrolytic cell. That is a very important thing. Already at the beginning of the class, where I have discussed about the electrochemical cell, there is the several cell, electrochemical cell and the electrolytic cell. The electrochemical cells means we will get the current from the redox reaction. But electrolytic cell is the totally opposite, where we have to give the external potential to running the redox reaction. Okay, there some nothing redox reaction is happening when we are not putting an external potential, but when we are putting an external potential, then the redox reaction is happening. So this type of the cell is called actually electrolytic cell. But where this type of the electrolytic cell is used basically in industrial area, you see some papers, there is some papers is there on the electrochemistry research. There is some companies there, uh, uh, industry companies there, industry basically, they use that technique, they use the electrolytic cell. They basically what they do, basically they put the external potential from the outside, they put the external potential, that means they put the current actually, electric current from the outside, and they get the something from that cell. Okay, that is the point. So that from that concept they apply and they get the impure to the pure metal. How they are getting the impure to the pure metal, that is the thing in the electrolytic cell and the electrolysis process. Okay, now how, what technique they use, basically in electrolytic cell they dip the two copper wire. Okay, they dip the two copper wire in a aqueous solution of the copper sulfate. So this is a aqueous solution of copper sulfate. So basically we know that this is a left hand electrode and this is a right hand electrode, but in the electrolytic cell that will be the opposite. We know that that is the anode for that electrolytic cell, but for that electrolytic cell it will be the cathode and it will be the anode. Okay, that is the thing. But anode, in this anode we will get the oxidation reaction, in the cathode that will be the reaction. But it will be the negative charges and that will be the positive charges. That is the thing. So that cathode will be the negative charges and that anode will be the positive charges. So what is happening here, basically in the cathode it is a negative charges, but there will be the reaction. So in that condition, so here the aqueous solution of the copper sulfate equal is actually the electrolyte, electrolyte. Okay, so that is the electrolyte and that is the electrode they have used here. The copper is the two copper wire is there, but that is the cathode and that is the anode. The copper sulfate is there. So in that cathode, what reaction is happening? The copper plus 2 is taking the 2 electron and it is the forming this copper. That is aqueous. But in anode, we know that the oxidation reaction is happened. So what is happening? This copper electrode is going to this copper plus 2 electron is forming. So basically what is happening, you see that copper, that is electrode, that copper first oxidized to copper plus 2. Okay, that copper is first oxidized to plus 2 and giving the 2 electrons. Okay, so giving the 2 electrons, and there is a electrolyte. So this electrolyte also of the copper sulfate is there. So in this electrolyte also copper plus 2 is there. So this copper plus 2 taking this 2 electron and it is forming the copper. So here we are lost the copper and also getting the copper. So basically what is happening, copper to copper is forming. This copper first oxidized to copper plus 2, and in this condition, in this electrolytic solution, this copper plus 2 is taking the 2 electron and it is forming the copper. So basically we are getting this copper to copper, but both copper are the difference. Why we are saying why we are saying that both copper is different? Here you see, so in that anode the oxidation reaction is happening. Here the copper is oxidized to copper, copper plus 2, but which copper? That copper, this copper wire. But this copper actually is pure, that is not a pure. Okay, so from that impure copper we are getting a pure copper, so that actually concept, so this concept actually industry that apply. Okay, so there are some industries there, this concept, this electrolytic cell concept they apply and they get impure metals to the pure metal. From that impure metal just oxidized and reduced, they get the pure metals. So from that concept, with this concept they apply and they get the pure metals. Okay, so this is the thing. So this is the electrolytic cell and the electrolysis is happening, but how much amount of the electrolysis is happening, that actually determined by this Faraday's law. Michael Faraday was the first scientist who described the quantitative aspect of the electrolysis. Now the Faraday's law is there. There is the two law. The first law is that the amount of the chemical reaction. So this redox reaction is happening. So the how much this chemical reaction is happening, that actually proportional to how much potential you are giving from the outside. So if you say the first law, the amount of the chemical reaction which occurs at any electrode during the electrolysis by a current is proportional to the quantity of the electricity passed through the electrolyte. Okay, here it is saying the quantity of the electricity. So quantity of the electricity, how much electricity you are putting from the outside, according to that, that amount of the chemical reactions will be happened. Okay, so that is the first law. Second law, they are saying that the amount of the different substrate liberated by the same quantity of the electricity passing through the electrolytic solution is proportional to their chemical equivalent weight. Here you see, here you can see that we are getting the copper impure to the pure copper. So how much copper will be the pure? How much pure copper we will get? That is actually proportional to the chemical equivalent weight. That is the chemical equivalent weight. So this chemical equivalent weight is nothing, that is the atomic mass by number of electron is required. Number of electron required for this reaction. Okay, so that is the thing actually. That is the thing. So this chemical equivalent weight is proportional to the how much amount of product we will get. So from that we can write the the Faraday's law, Q equal to I into T, where the Q is the electricity in Coulomb and I is the current in ampere and T is the time in second. So these are the thing, and also so from that concept, this Coulomb the C equal to the Coulomb C equal to how much, this Faraday constant equal to 96487 Coulomb into mole inverse. Okay, so from that concept we will start in the next class. In the next class will be the last class of the electrochemistry. Just in the next class I will discuss the conductance. Okay, this is the very important things, the conductance and also the corrosion. So these two things I will discuss in the next class. Here I will stop the class. If you have the any problem about the concept, about the teachings, and also I am giving the some MCQ, you will have the some problem you can discuss in the next class.